Thank you for the introduction. Good afternoon. I'm Vishnu Dasu, and I'm a PhD student studying computer science at the Pennsylvania State University. And today I'll be presenting a paper titled Privacy Preserving Data Deduplication for Enhancing Federated Learning of Language Models. So it's a well-known fact that the quality of training data has significant impact on the performance of machine learning algorithms. In the case of vast text data sets commonly used to train language models, duplicated or repeated text sequences are prevalent, and these negatively impact data quality. Prior work has shown that these duplicates adversely affect LLMs by increasing perplexity and training time. For example, they show that the C4 dataset has a 61-word sequence that is repeated verbatim about 61,000 times, and deduplication improved perplexity by up to 10%. Here, perplexity is a metric used to measure how good LLMs are at next word prediction, and the higher perplexity usually denotes worse performance. Now, in federated learning, we have a single server that orchestrates the training of a global model on data sets held by multiple clients. And the server only aggregates gradient updates and cannot see the client data. Similarly, the clients cannot see each other's data sets. The prior work deduplicates data in centralized setting, which is trivially private, as there's only one entity. And the question we aim to answer in our research is, how do we deduplicate data sets in federated learning while preserving data privacy? So now I'll be talking about the contributions of our work. Our solution, which we call Efficient Privacy-Preserving Multi-Party Deduplication, or EP-MPD, is based on a new variant of the private set intersection or PSI protocols. EP-MPD securely removes all pairwise duplicates from data sets held by two or more clients in federated learning. And along the way, we introduced the notion of group private set intersection, or GPSI, which is used as a building block for EP-MPD. Now I'll be talking about some background about private set intersection protocols. A PSI protocol lets two mutually distrustful parties come to the intersection of their private sets such that nothing beyond the intersection is revealed to each party. Consider the following example with two parties, Alice and Bob. Alice has elements 1, 2, and 3, and Bob has set elements 1, 3, 4, 5, and 9. After the PSI computation, both Alice and Bob learn that the intersection is 1 and 3. However, Bob must not learn that Alice has 2, and similarly, Alice must not learn that Bob has 4, 5, and 9. So now I'll be presenting the new notion of group PSI that we introduce, which is used as a building block of our solution EP-MPD. The group PSI protocol operates on two groups of users or clients, and this is different from the PSI protocol, which is in a two-party setting. The group PSI allows all clients in one group to find the pairwise intersection of their set with the set of all clients in the other group. The following expression here highlights the functionality of a GPSI protocol. The function takes two arguments. The first argument are the sets belonging to all clients in the first group, which we denote here as G0. And these are S01 to S0M, where 0 denotes the first group and 1 to M denote the M clients in the first group. And the second argument are the sets belonging to the clients in G1, which is second group, and S11 to S1M denote the sets of the clients in the second group, where 1 is the second group, and 1 to M are the M clients. And the output of the GPSI protocol should be a vector for each client, where the vector contains the intersection that this client's set has with the sets of the clients in the other group. So now that we've introduced the notion of what the group PSI is, we developed two protocols that meet the requirements of group PSI. In the interest of time, I'll be briefly explaining these protocols, and I encourage you to refer to the paper for concrete details and security proofs. So the first protocol is called EGPSI1, and this protocol relies on private key encryption. On a high level, the clients in both groups first engage in a pairwise key exchange, and then they compute the pseudorandom permutation of their set elements to encrypt them, and they share these encrypted elements to a trusted execution environment, or TEE. The TEE can then be used to find the shared encrypted data, and it sends the corresponding shared data to the clients in each group, and the clients can decrypt the shared data to find out what they have in common with the clients of the other group. And the EGPSI1 protocol requires the TE to only find the shared encrypted data, and it, in general, requires relatively little processing time. The other protocol, which we call EGPSI2, relies on public encryption, and it uses a TE to compute the oblivious pseudorandom function or OPR evaluation of its set elements. So once the clients encrypt the data using OPRF, then they can exchange their encrypted elements with the clients of the other group to find out the common intersection. And this requires more processing time, but the TE is only required in the beginning to compute the OPRF evaluation, and once that is done, we don't need a TE anymore. And at this point, I'd like to point out that our trust and security assumptions about the TE are quite conservative, and the TE can be replaced with any semi-honest server that does not collude with the clients. So now that I've introduced the notion of the group PSI and we have developed two protocols that meet the requirements of group PSI, I'll explain how the group PSI can be used as a building block to create our EP-MPD solution, which can remove all pairwise duplicates. So EP-MPD first constructs a binary tree where the leaf nodes of the tree represent the various clients taking part in federated learning. And at each level of the binary tree, we form clusters of clients where the left and right subtrees represent two groups in the group PSI. And then starting from the lowest level, EP-MPD iteratively invokes group PSI on the clusters as we move up the tree. And once we reach the root of the tree, we can see that all pairwise duplicates have been removed. So let's have a look at a concrete example with 8 clients. And with 8 clients, we have a binary tree with 3 levels, and this is represented by the figure on the right side. At the lowermost level, we have 4 clusters, and each cluster has 2 groups with 1 client in a group. And for example, if you look at the leftmost cluster, you have client C1 in group 1 and client C2 in group 2. And C1 can engage in the group PSI protocol to find the intersection it has with C2 and remove the duplicates. Now, at the second level, we have 2 clusters, and in this cluster, there are 2 clients in each group. And once again, if you have a look at the first cluster, clients C1 to C2 in the first group can find the intersection that they have with clients C3 to C4 in the second group using group PSI, and then they delete their duplicates. And finally, at the root level, we have only 1 cluster, and we have 4 clients in each group, and clients C1 to C4 in the first group can remove their duplicates that they have with clients C5 to C8 in the second group using group PSI. So now that I've defined how EP-MPD can utilize the group PSI as a building block to remove our pairwise duplicates, I'll talk about the end-to-end functionality about how EP-MPD can be used in federated learning. So in the first step, each user in the federated learning protocol removes the local duplicates by simply performing local deduplication, which is trivially private. And in the next step, after all local duplicates have been removed, the users run the EP-MPD protocol to remove all pairwise duplicates that exist across the datasets. And finally, once all the pairwise duplicates have been removed, the clients can then join any federated learning protocol of their choice to proceed with model training. So now I'll be talking about the experimental evaluation of our protocol. We implement EP-MPD in Python with AES 128 CBC as a pseudorandom permutation for EGPSI1, and we use EC-OPRF for EGPSI2. And we create a federated learning setup to fine-tune LLMs with 10 clients, and we evaluate with 7 text data sets and vary the percentage duplicates up to 30%. We then compare the perplexity and GPU training time before and after deduplication with EP-MPD. And we use the GPT-2 medium and GPT-2 large language models. So this table here highlights the performance of EP-MPD with the both variants of the group PSI protocol against the naive approach that relies on two-party PSI. And if you recall the problem at hand, which is to remove all pairwise duplicates, this can also be done by running a two-party PSI protocol n choose 2 times, where n is the number of clients. For this experiment, we vary the client count from 10 to 50 and fix the dataset size to 2 to the power of 19 elements. And we can see that as we increase the number of clients, the performance speed up that is observed with EP-MPD becomes more noticeable. And we observe up to a 14 times speed up with 50 clients for EP-MPD that utilizes the faster eGPSI1. And naturally, the EP-MPD variant that utilizes the slower eGPSI2 based on oblivious pseudorandom functions, it's not as fast, but it's still faster than the naive approach of applying two-party PSI. And in this table, we analyze the improvement in perplexity after deduplicating with our protocol. So the rightmost column highlights the best perplexity that is observed on fine-tuning the language models on the deduplicated data sets using EP-MPD. And the remaining 3 columns show the perplexity where, for different duplication percentages, which is 10 to 30%. And you can see the general trend is that the perplexity tends to increase as we have more duplicates in the data set. And the blue text in the table highlights the best improvement in perplexity that we observe, which is for the place data set in GPT-2 medium. And that's about 19.6% improvement in perplexity. And similarly, we have the same results for the total GPU training time. And once again, the rightmost column denotes the best training time, which is observed in the deduplicated data sets. And the highest improvement in this case is observed for the Sonnets data set with GPT-2 medium, which is about a 27.9% improvement in training time. So in conclusion, we develop EP-MPD, a protocol that efficiently removes all pairwise duplicates in federated learning while preserving data privacy. And we observe up to 19% improvement in perplexity and up to 27% improvement in GPU training time. And for future work, one could consider removing near duplicates, where a near duplicate could be parts of a sentence repeated instead of the entire text sequence. That's something that we do not consider in our work currently. Thank you.
Thank you very much. So is there any question? Yeah, one question.
Hi, thank you for your presentation. My name is Claire Van Zwieten, again. So I'm going to ask you the same question I asked the other presenter. What is the human impact of your research, and how does this project potentially affect someone who maybe, I like to use the example of your neighbor. So how would this affect their life?
Yeah, thank you. That's a good question. So let's take the example of Google's keyboard prediction. They actually use federated learning to train their model for keyword prediction. And one problem of duplicates that I didn't exactly mention in our research is that duplicates can increase memorization language models, which can also pose privacy risks as it increases the success rate of membership inference attacks or data extraction attacks. So by performing this deduplication, you can decrease the chance of privacy attacks on your data when machine learning models have been trained on them.
Thank you.
Yeah.
Okay, any other question? I also don't have any questions, sorry.
Yeah.
Then thank you again for your talk, and maybe thank the author again.